The Newton-Raphson method is an iterative numerical analysis algorithm used to find the real roots of a function f of x equals 0. It uses the calculus-based approach of finding the tangent line of a function at a specific point to approximate its x-intercept. The formula calculates a successive approximation x sub n plus 1 from the current guess x sub n, the function value, and its derivative. This method features quadratic convergence, meaning the number of correct decimal places roughly doubles with each correct iteration. However, it fails if the derivative is 0 or if the initial guess is too far from the root, causing divergence. The equation for the Newton-Raphson method is shown here, where f is the function that is being analyzed to find its root. F prime is the derivative of that function, x sub n is the initial guess of the value of that root, and x sub n plus 1 is the approximated root that will be used as x sub n in the next iteration. To find the root of the example function y equals e to the x minus 2, we must first establish its derivative. The derivative of the natural exponential function e to the x is itself, and the derivative of the constant 2 is 0. This yields the foundational components necessary to construct our iterative algorithm steps. Substitute the function and its derivative directly into the Newton-Raphson equation. We can algebraically simplify the expression to minimize operations and streamline the subsequent calculation steps. Establish an initial guess x sub 0 equals 1, because e to the 0 equals 1, and e to the 1 is approximately 2.718, indicating the root lies between 0 and 1. Evaluate the simplified formula with x sub 0 to calculate the first refined approximation, x sub 1. Input the newly found x sub 1 value back into the tracking formula. Process the arithmetic to yield the next, closer approximation, x sub 2. Repeat the setup substituting x sub 2 to track deeper convergence. Calculate the value x sub 3, which brings the approximation near its limit. We verify our numerical result by computing the exact root using log laws, where x equals ln of 2. Comparing the outcomes demonstrates that our third iteration matches the true solution to 4 decimal places.